not the parents. Well, actually, well, again, I'm ahead of myself. Which one of the children do we know they're the genotype for sure? The disease kid, because if you have a recessive disease, what does your genotype have to be? It's got to be little q, little q. Remember, if somebody shows the dominant trait, the non-disease state, you don't necessarily know right away, because both of these will give you non-disease. As long as you have at least one functional copy of the gene. And so at first, we might think, well, we don't know their genotypes. They could be big Q, or big Q, little q. If, let's say, these are the parents, is it possible for them to have a kid who has little q, little q? No, because if you do the Punnett square for this, you can't get a little q kid. It just can't happen. The closest you can get would be a big Q, little q kid. So we know those aren't the parents. Is it possible to have these as the parents? What would be wrong with that? Well, there's a couple things wrong. What would we know about, what would this parent ought to have? They would have the disease, right? So that doesn't work. And obviously this wouldn't work because there's no little q's at all in the parents, and somehow the kid got two little q's. That can't work. But there's one thing that does work. That would allow both parents to be healthy, but to have a child who's has the disease. Like so. All right. Now, maybe I should do the Punnett square for that one real quickly. So each kid they have has a 1 out of 4 chance of getting the disease. But if the kids don't get the disease, there's two possible genotypes they could be, big Q, or big Q, little q. And so over here, we don't exactly know what the genotype of these kids are. It might be that, or it might be that. So therefore, when you're filling in the genotypes on these pedigree charts, in some cases you'll know the exact genotype, and in other cases you'll just have to guess. But you do know that it's not dominant. That's about the only thing you can really definitely conclude. Okay, here's another example. Could this be a dominant disease? The answer is yes, it might be. Here's the parents. What do the kids look like? They've got 3 sons. Poor people. All right, so if it's a dominant disease, what does her genotype have to be? Little q, little q. You remember, for dominant diseases, if you don't have it, you have to be little q, because the dominant allele gives you the disease. And this boy's genotype, little q, little q. What is this parent's genotype, this dad's genotype going to be? Big Q, little q. Yes. Now, if you were saying, well, it could be big Q, technically you're correct, but remember what I said, for dominant genetic diseases, they're so rare, anybody who has it just assume it's big Q, little q. And so we'll do the same thing to the boy right there. And this works, because if you do the Punnett square for the parents, all those kids are possibilities. You can have kids who don't have the disease, little q, and kids who do have the disease, big Q, little q. So for this chart, where the disease is not skipping a generation, it's showing up both in the parents and the offspring, it's possible that it's a dominant disease, but it's also possible that it's a recessive disease. Let's see if we can make that work. If it's a recessive disease, so you get it by being little q, what's dad's genotype? What's this boy's genotype? Little q. Could mom be big Q? Anything? No, because if you do that Punnett square, they can't have any diseased kids. Everything's going to be big Q, little q. And that's not consistent with the chart. One of the kids does have the disease. So what should mom be? Big Q, very good. You guys are getting it. So she's a carrier of the disease. And if we do that now, we can make the chart work. Some kids will have the disease. That's not good. Oh, actually, if that's the case, we can actually fill this in. What are these two boys? They've got to be big Q, little q. Excellent. All right, so anyway, getting back to here, if the disease appears in every generation, it, in theory, can be dominant or it can be recessive. You don't really know for sure. Now, when you see these actual pedigree charts, sometimes they'll have 3 or even 4 generations. And even though in this generation you can't necessarily tell whether it's dominant or recessive, perhaps when these kids start having kids, you'll be able to figure out whether it's dominant or recessive. And one of the worksheets you'll be doing today is a sheet of pedigree analysis like that. And we won't do the details of this one right here, but just looking over it, go back. Just looking over this chart real quick, can somebody tell me whether it's a dominant or recessive disease? Recessive, why? It skips it skips a generation. The parents don't have the disease here, yet their kids show up with it. If it was a dominant disease, where did the kids get a dominant allele? Not from the parents. And here you see it again. None of the parents have it, but it shows up in some of their kids. So you can toss out the idea that it's a dominant disease because it is skipping generations. It has to be recessive. Whereas for this one, it shows up in every generation, so it might be a dominant disease, or it might be a recessive disease. But as you go through the chart, some of the generations later on down the chart may point out to the fact that it has to be dominant or it has to be recessive. And you'll cover that in the worksheet. All right. Well, let me cover one final topic and then I'll set you loose here. Certainly that. Getting back to something I glossed over the first time through. One of the things I covered in the lecture hall was to figure out how many gametes, different types of gametes, a person could make. If the person's genotype was this, focusing in on just the A gene, how many different types of gametes could they make? 2, right, because when you make gametes in meiosis, your sperm or egg cells become haploid, meaning each sperm or egg gets one of your 2 genes, and so some of those eggs or sperm would look like that, and some would look like that. If a person if we focus in on just these 2 genes, how many gametes could they make? 4, right. Remember how this works. You say that each sperm will get one A allele and one B allele, but which one of those is always random. And so that big A could link up with big B, or that big A could link up with little b. Or maybe the sperm will get the little a and the big B, or the little a and the little b. And So all of these can be made with equal likelihood. Something like that. How many? Oh, and another approach to this would have been just to say it mathematically. How many different ways can you get the A allele in the sperm? Two different ways, big A or little a. So you could say there's two choices there, two possibilities there. How many ways could they get the B allele? Well, the sperm can get big B or little b. So two different ways. And remember this idea, if there's the probabilities of two different things, you multiply them. And so there's 4 probabilities or 4 combinations that the sperm could be. What if I gave you something like this? What if I said, here's a individual's genotype. How many different types of sperm can they make? 8. Because there's 2 possibilities. Each sperm could get a big A or little a, and there's 2 possibilities. Each sperm could get a big B or little b, and there's 2 possibilities for the C. Each sperm can get big C or little c. So if you do all the combinations, it comes out to 2 times 2 times 2 is 8. How many different types of eggs could this woman make if we just focus on these 3 genes? 4. 2. How many different types of alleles could the eggs get for this gene? Just 1. All the eggs get a big A. How many different types of alleles could they get for the B gene? 2. How many different alleles could they get for the C gene? 1. Just big C. And so it comes out to, if we just focus on those 3 genes, she can only make 2 types of eggs. Big A, big B, big C, or big A, little b, big C. And one of the worksheets you'll be doing today is based on that concept. And this thing here on the overhead, which is from your notes, is related to what I just showed you, but it's not exactly the same thing. This thing that I'm showing you here allows you to predict what the chances of an offspring with a certain genotype are given the genotypes of the parents. And you've been doing this, we did this in lecture using the Punnett squares, but this is essentially a mathematical approach where you don't draw the Punnett squares, you can grind it through on pure mathematics. And so it says this: if the parents are big A, little a, big B, big C, little c, and big A, little b, little c, little c, what's the chance that they can produce an offspring that's big, little a, big B, little b, big C, little c? How often will they produce that particular genotype offspring? Well, what this tells us is you can figure out the odds of the big A, little a cross producing little a, and multiply those by the odds of a big B, little b cross making big B, little b, and multiply that by the odds of a little c, big C, little c cross making big C, little c. And again, it comes out the idea you can just multiply the different probabilities together. So what's the odds of a big A, little a cross giving you little a? 1 in 4. If you do the Punnett square, there's a 1 in 4 chance that big A, little a crossed with big A, little a gives you little a. What's the chance that a big B crossed with little b gives you big B, little b? 1. The Punnett square would be all big B, little b. So 100% chance equals 1. And what's the chance of big C, little c crossed gives you big C, little c? Not 2, 1/2. Maybe I should draw that one out. Big C, little c, little c. Like that. So 2 out of 4 or 1 out of 2 chance that you get a big C, little c offspring. So just multiply all the odds together. 1 times 1 times 1 equals 1 out of 8. And so for these two parents, you could mathematically predict that each offspring they have has a 1 out of 8 chance of being little a, big B, big C, little c. Let me give you one problem and then we'll I'll turn you guys loose here. This is a slightly different problem, but what's the chance that the offspring will show the dominant phenotype for A, dominant phenotype for B, and dominant phenotype for C? So it's the same concept, but try to think of what the phenotype chances would be.